In the next subsection, I want to talk about Huffman codes, which will be, in a way, the ultimate solution to character encodings. It all starts with the observation that characters come with different frequencies. So here's a list for typical English prose, how often each character occurs. Oh, surprising. Z is less frequent than Q. I mean, this may depend on the text, but if you take a big corpus of text, you will get some frequencies. And you see that they are quite uneven. So it looks like for compression, you definitely want to assign E a short code word and something like these infrequent ones a longer code word. You don't want to go completely crazy about making those 100-bit long or something like this, but you should try to make them longer than the more frequent ones. And if you remember what the Morse code did, it was exactly like that. E was just a single dot, and then the less frequent characters were longer, up to 5, 6 tones. So Huffman coding is all about getting a principled answer to how should you choose the code words. To make this a bit more clear, suppose we have our alphabet. So sigma is the source alphabet, because the coding alphabet will always be binary now for our Huffman codes. And we assume we have some weights. So we know these can be frequencies, but in principle here we just allow any real numbers. So this just tells you how important this character is relative to others. And you want those characters with large weight to have a short code word because they appear more often. Think of the weights as frequencies or probabilities. The goal of Huffman coding is to compute a prefix-free code. So code words for all the characters. In other words, if it's prefix-free, it's a code trie that minimizes now a specific quantity, and that's the coded text length if you weight each character with this weight W. So we're minimizing this quantity. We sum over all the characters. How long is the code for this character times its weight? If you think about a fixed text and you choose W as how often does the character occur in the text, then that's exactly the size of the coded text. Right, so to get this, we want to choose W of C as the number of occurrences of this character in the text. I should say source text, I guess, but you know what I mean. Okay, that's the same as I just wrote down. And in a sense, if we minimize this coded text size, that's clearly the best possible character-wise encoding we can hope for. Because we explicitly say, let's pick the code that minimizes that. So that's the code that gives you the minimal coded text size. That seems like an ambitious goal. And if you think about back to the lesson about Kolmogorov complexity and how these things are all quite tough, maybe this is asking for too much. And then even if we can't find such codes, can we find them efficiently? That's even more ambitious. It turns out both things can be done in this case. Because we restricted our attention to character-wise encodings, the world is a bit more manageable. So even a very simple approach that is greedy or myopic suffices. And we'll go through this in a second. So greedy algorithms in general try to do a locally optimal move and then fix that for good and continue from there. And we'll see how Huffman's algorithm for computing the Huffman code is doing exactly that. The greedy step is you find two characters in your alphabet, A and B. So these are just called A and B. These are variable names, right? We find two characters and name them A and B that have the lowest weight among all the characters in our alphabet. That's the greedy step. Now remember, low weight means we want to assign them a long code word. So what we'll do is we will encode them with some prefix yet to be determined and one extra bit that distinguishes A from B. And by doing this, so we set the code word of A as U0, B as U1, but U is not clear yet, so we'll have to figure this out. And the way to do it is that we replace in our alphabet the two characters A and B by an artificial character that consists of both. So I use the same notation for boxes of characters that we've seen for the DC3 algorithm for suffix sorting. This is just my way of saying this is a new symbol and it's supposed to represent A and B, but it's just a name, okay? And important, we assign this new character the weight, which is the sum of the weights of A and B. And then we recurse. So we don't know what U is, this prefix that we'll assign to A and B, but we'll find out recursively because now we have made the alphabet one smaller. We removed two characters and added one new. So if we recurse and find a Huffman code for the remaining alphabet and its weights, this will come back with a code word for this new character AB, and that's our U. That's the shared prefix that we add to them. Okay? If you've seen this before, this might not be the way it was described. There's another way that you'll see in an example in a second that you might recognize. Before we go there, I want to point out that you also know an efficient way to implement this strategy. This step one sounds like you have to, in each iteration, so sigma times in total, you have to find the two minimum weight characters. But if you're smarter than just doing this iteration each time from scratch, you keep the characters in a priority queue. And then this first step is just two delete min calls. So at the same time, you get the two characters for the minimal weight and you get them out of the data structure. And then you insert a new character with the sum of weights. So that nicely fits the priority queue abstraction as we've learned about in Unit 2. Let's see a small example how this looks like. And it's visualized here by computing this code trie. That's usually the way this is explained. So here's a little source text. It has these 4 characters, and they appear with frequencies 1, 2, 1, 4. So you start with your characters, each as a singleton leaf in the yet to be completed code trie. The first step is to find the two with smallest weight. So these two, they have minimal weight in this example. And now Huffman's algorithm says recurse on this and the character EO that you form. And then at some point, you will know what is the common prefix of the code words for E and O. Another way to express the same thing is say, we don't know where this is eventually ending up, but as a code trie, there's one node where these two are branching off, one with a 0, one with a 1. And the fact that they share a prefix means this can later be part of a bigger tree, but we're not there yet. And we assign this entire tree now the weight 2, which is the sum of the weights we've previously had. That's the first iteration. Second iteration is again find the two partial tries with minimal weight, these two, and combine them into a single trie, where again you have a new node. It has two edges, 0 and 1, and they both lead to the two previous little trees. Okay. And here in this example, one more step where nothing really is chosen, so only two things left, so you only have to lump them together. If you were to revisit this first step where we grouped E and O, you now see that U is just 2 zeros. But the way of constructing these tries, or keeping these partially constructed tries and merging them, is a convenient way to achieve this without ever doing the explicit recursion. It's very natural to do this in an iterative way bottom up. because we're using this notation in the tutorials, I want to stress that this is just the EO character as it was in the previous slide. So that's the new character that corresponds to E and O. But we can also do this at the next level. So we have EO with a box around, and then we combine this with L and put a bigger box around. I'm showing you this because this is a concise way to show the tree without drawing the tree. So this might be convenient to quickly sketch this, say in an exam, right? And then one more go. We have our EO, which is boxed together with L, which again is boxed together with S. And you can go from this representation of the tree to this nested boxes representation by taking away the outermost box, and then there's a left and a right part, which have to be the biggest boxed parts. So if you wanted, you could draw a line, but it's not really necessary. So then the left box is what you reach with 0, the right box what you reach with 1, and then you unpack those boxes recursively. So the result of this process is called the Huffman tree, which is nothing else but the code trie for the Huffman code. So this contains all the code words for those 4 letters. And if you want, you could write down the table that we've had before. Remember, for encoding, it's more convenient to use this table. So E has 0, 0, 0 as a code word. L has 0, 1. O is 0, 0, 1. And S is just a single 1. And so if you encode lossless using this, you would first put an L, that's the 0, 1. Then you would put an O, 0, 0, 1. That's where these come from. And then you have 2 S's, that's 2 1s, and so on and so forth. And if you were to decode this, you want to use the trie again, as we've seen before in the other example. So you walk down the trie and find in the leaf what's the character it corresponds to. What's interesting, even on this tiny example, if you compute the compression ratio as the number of bits we needed here, turns out to be 14, divided by what you would need if you represent this tiny alphabet with 2 bits per character, the kind of the traditional or natural way. If you have an alphabet of 4 characters, you use 2 bits per character, then you would need 16 bits. So even here you achieve a compression ratio of 88%. Even though this is a really tiny example. So it seems Huffman codes work. This is a remark that is essentially just relevant for assessments. Sometimes if you build the Huffman tree, there are ways where you have to break ties, and either way would be fine. It's just, I want you to follow a specific rule so that you all arrive at the same result. For example, even here at this first step, there's the 2 elements. They have the same minimal frequency. So which way do you put them in the tree? Here I put E left and O to the right, but I could have done it the other way around. There's no rule in the Huffman algorithm, as I told you, as I described it in the previous slide, which way to go. Both is kind of fine. There's a tie-breaking rule for that, which says when you have 2 characters and you find the smallest, when selecting the characters and there's more than 2 that have minimal frequency, then we select the ones with smallest order in the alphabet. That's the first rule. When we combine 2 trees of different values, then we place the lower on the left. And the third rule is what applies to this example when we combine trees of equal value. then again, we break the tie by what is the minimal symbol in either tree. And so E comes before O in the alphabet. That's why E was left. Okay? So just practice these 3 rules. We'll do this in a tutorial question. So you'll have ample opportunity to practice these. That's just the type breaking rule I want to follow for the course. It doesn't make any difference. You could use a different one. The compression result would be, the compression ratio would be the same, but you get different codes, and that's just confusing everyone. So we've seen how to compute a Huffman code. What we haven't completely discussed is how to compress with Huffman. And it turns out there's a few different options, but the easiest one is you do a 2-pass procedure over the text. In the first pass, you just keep account of how often each character occurs. After that, you construct the Huffman code as we've just seen it. And remember, you need the weights to go to compute the Huffman code. And so this first phase is about gathering the weights. Then we compute the Huffman tree. Then we have to somehow encode the Huffman code as well as part of the coded text. And I omitted this here because you want to do this in a somewhat smart way to get good compression ratios, but then it gets quite intricate. The practical solution is to further restrict what Huffman trees are used. So essentially, you do another step after this. I don't want to get into this detail. But I want you to remember that you have to store the Huffman code as part of the coded text. It's not really something you can get around. And then the second pass, once you have your code, you do a second pass through the text and encode each character using its code word, as we've seen in the example. To decode this, you read the code that someone encoded in the coded text. Again, we won't talk about how to do this in detail. There are simple ways and there are smarter ways that I don't want to get into. And once you have the code, you can start the decoding as we've seen in the examples. You follow in the trie down the path until you reach a leaf. Then you know the first character. You jump back up and continue from there. I note something that will be reoccurring in other compression algorithms. Decoding is simpler or also faster than the encoding step. And usually that's because in the encoding step, we have to analyze, we have to do this recon stage where we have to find the redundancies in the text to exploit them, whereas the decoding doesn't have to do that. It's just told what to do. Okay, before we finish with Huffman, I want to convince you that this is not just a random procedure that seems to work well on an example, but indeed computes the best possible code. As I said on the slide, this is what we want. I want to quickly convince you that this is indeed the case. So we want to prove this theorem. I spelled it out here a bit formally, but let's digest it one bit at a time. We start with a given alphabet and some weights. Then the statement is that the code that we've seen, the algorithm for Huffman's algorithm, computes code words that minimize this expression, same expression as we had it before. I'll abbreviate with L of E because this will appear in the proof many times. We sum over all the characters, the length of the code word times the weight of that character. That's what we want to minimize. And we minimize this among all possible prefix-free codes for this alphabet. So as long as you insist that you want a code that encodes one character at a time, Huffman gives you the best possible way to do that. And the proof is an induction over the size of the alphabet, which is natural because the algorithm also is recursive over the size of the alphabet. It calls itself on a smaller alphabet. So first of all, we should do an induction basis. If I have just 2 letters in my alphabet, Huffman will just assign one the code word 1 and the other code word 0. And that's also the only prefix-free code that we have. So there's nothing really to do, and Huffman does what is claimed. It computes the optimal code among one option. So it works for 2 symbols. Now the induction hypothesis is, suppose it works up to a certain number of symbols. And now we look at the next bigger alphabet size, sigma. And so the sketch only shows the inductive step, where sigma is at least 3. And now suppose we're given an optimal code. This is a proof. It's not a way to compute it. So I get to say, you give me the code and I'll work with it. E star is an optimal prefix-free code for my alphabet with its weights. So because it's a prefix-free code, it can be shown as a trie, a code trie. And because it's a binary trie, there must be 2 leaves, 2 sibling leaves in this trie that are the lowest level. So no matter how you stop the tree, at some point there must be a node that has 2 leaves, and that's at the deepest level. Otherwise, there would always be a dangling edge left. So we can always find these 2 leaves, x and y, at maximal depth. And that's true for any optimal code. And now I'm modifying this code. So remember, a Huffman code starts by picking the 2 characters of minimal frequency and makes those siblings. The optimal code might not do that. It might do something different. So what we'll do next is we find the 2 lowest weight characters, A and B, as in Huffman's algorithm, and we swap them with whatever's in x and y in the optimal code. There could be other characters. Maybe the optimal code found a smart way to put another character down there. But if I swap these down, if you look at the sum up here, we make the encoding for A and B potentially a bit longer. But whatever was in x and y before, we make the code word potentially smaller because we move it up in the tree. And this net change is moving something up releases weight, and moving something down costs us weight. But the thing we move down has minimal weight. So we definitely can only gain by doing this swap. And since the code was optimal, the new code must be still optimal. It can't be better than optimal. So we find the 2 characters A and B with minimal weight, and we swap them with x and y. And that still leaves us with an optimal code. And now comes the trick, which is similar to Huffman's algorithm. We try to find an optimal code for sigma prime, which is our alphabet, where we take out A and B, and we put in this new lumped together character. And also assign the weights. The weight of this is the sum of the weight of A and B. And so if we have an optimal code for this sigma prime, we can get an optimal code for sigma by just replacing this leaf for A and B with the little tree that branches out to A and B. Right. So in a picture, there was some deepest node here where we have these leaves x and y, and then we replace this by this x and y lumped together, and we can always go back and forth between these steps. So this was for sigma, this was for sigma prime. The rest above, this is the same tree. So the only change I make in this optimal code for sigma prime is replace the leaf for AB again with this little tree that branches off to A and B. And so we assume we made the alphabet 1 smaller, so we can use the inductive hypothesis that Huffman computes an optimal code for sigma prime. And so that together gives us an optimal code for sigma that is found by Huffman's algorithm. We exactly mimic how Huffman's algorithm would have done the first step. We pick the 2 characters from minimal frequency and put them together. And so by the inductive hypothesis, the code that Huffman finds for sigma prime is optimal. And the way it modifies it into a code for sigma, leaves it optimal. That concludes the proof for Huffman.